Hi everyone, I'm Junhong Wang from Fudan University. Today I'm going to introduce our work on when, where, and how does it feel, a spatial-temporal visual analytics approach for interpretable object detection in autonomous driving. Autonomous driving has grown rapidly in recent years and has the potential to change transportation systems and even human society significantly. Object detection algorithms play an important role in the perception stage of autonomous driving system. One such challenge is that most algorithms are inherently black boxes that provide little information that would explain their decision-making process. We researched the current state of development in related fields and summarized our requirements. Accuracy in the field of self-driving object detection is increasing, and the interpretability is in high demand. Most interpretability work focuses on CNN. Since autonomous driving happens in a spatial-temporal environment, it is important for model developers to understand the spatial-temporal context of models. Some open-source tools can support visualization-based exploration, verification, and presentation of spatial-temporal data. However, these tools are largely strong in the presentation, but weak in in-depth analysis. We propose an interpretable visual analytics framework and visual analytics system integrated with spatial-temporal information and CNN features to improve the work efficiency of model developers. First of all, through the interactions with domain experts and literature analysis, we summarized our design goals as to help developers understand when, where, and how an object detection algorithm fails. Based on our goals, we abstracted relevant data into three categories: model data, spatial data, and temporal data. Design requirements are based on the goals and validated by domain experts. Following the requirements, we designed a visual analytics system with a proposed exploration workflow. The visual analytics system includes two modules: micro-interpreting module and macro-interpreting module. The micro-interpreting module visualizes module features as features view. Feature information inside the model is processed and visualized as density map. It provides an intuitive insight into what is captured by the model and its relation with detection results. For example, the left image has 5 objects with green bounding boxes, but only 3 are detected with red bounding boxes, consistent with 3 parts of high edge activation values and low internal activation values in the density map. In the right image, 2 objects are both detected consistent with 2 parts of activation regions. Object projection visualizes the processed features of each detection and corresponds to an accuracy metric, IOU, or two-dimensional coordinate system, providing an overview to observe the relative distance and distribution of object-level features, and further answers the question of how the model feels. The macro-interpreting module mainly focuses on model analysis from temporal and spatial perspectives. Each perspective is supported by a view. Temporal view includes autonomous driving vehicle states and object-level density maps to provide insights into when and how. Velocity, acceleration, and wheel steering data from the GPS monitoring of the vehicle is drawn. Object-level density maps visualize the detection sequence of objects from the checklist, as well as the detection results from the model. This chart shows the correlation between object-level features and detection results in temporal distribution. Spatial view includes scene and trajectory to provide insight into where. Scene is a 3D spatial stereogram drawn with raw data that contains the point cloud data, latitude and longitude information, and checklists of labeled objects. 3 view modes are provided in this chart. Trajectory combines the relative position in the bird's eye view from checklists and detection results and arranges them in the order of detection. This chart shows 3 kinds of trajectory patterns including approaching, turning, and driving away after turning. Each of these 3 views provides one or more perspectives on answering the question of when, where, and how. The interactive exploration process is illustrated in a guidance example. We have annotations on each view to guide users choose some view, which can be 1 or 2 according to the design requirements as an overview. Then zoom in and filter. Other views would be shown accordingly. To evaluate our workflow and system, we did a case study and expert study. In the case study, we chose the KT dataset, a popular and well-known dataset in autonomous driving. We present 2 case studies with 2 different autonomous driving scenario sequences. In the expert study, we conducted an interview study with 7 experts to evaluate the usability and effectiveness of our system. Let me present one of the case studies. This case shows autonomous driving on a highway with the presence of other objects. We click this sequence which has unsmooth activation boundaries and find the time corresponding to the orange border position on the timeline. We find the actual location of these objects in the map by looking at the selected position in trajectory. We drag the timeline and combine the real things in the scene and image to understand this scenario. We find that sequence with uneven activation boundaries is associated with bad detection results, and close proximity to the pedestrian and the other cyclists, which may provide micro and macro interpretability to the failed cases. And finally is the conclusion and discussion of our work. For generalization, our approach can be extended to the other interpretable work by considering contextual factors. Through the interview with experts, more work is needed to meet the needs, such as multi-scale network features, light, weather, and object color. To improve the scalability of our system, measures like better system architecture or effectiveness data aggregation methods can be considered. To summarize our work, we propose a visual analytics approach and develop a system to provide in-depth visual analysis of object detection models in autonomous driving. We expect our research will offer some new ideas for the interpretability of object detection. Thanks.